Electric cars are available in different drivetrain options. The placement of the electric motor plays a very important role in the power delivery and purpose of the vehicle. EVs can come in different configurations, such as a single motor, dual motor, 3-motor, or a separate motor for each wheel. Some EVs like Tesla uses a single or dual motor setup. The wheels are directly connected to the motors by eliminating transmissions. The Model S Plaid and the Tesla Roadster come with a 3-motor setup. 2 individual motors drive each of the rear wheels, and a common motor driving the front wheels. The Rivian R1T and R1S has a separate motors for each wheel, however they are inboard and not hub motors. This setup will increase the agility and handling of the vehicle. Before getting into these motor configurations in details, let's understand how an electric motor works inside an electric car. An electric car motor works using a physical process that consists of using a current to create a magnetic field at the fixed part of the machine, called the stator, whose displacement sets in motion of a rotating part, called the rotor. Understanding how an electric motor works is pretty simple. Here's the simplified explanation of how a 4-pole 3-phase AC induction motor works in a car. It starts with the battery in the car that is connected to the motor. Electrical energy is supplied to the stator by the car's battery. The coils within the stator, that is made from the conducting wire, are arranged on opposite sides of the stator core and act as magnets in a way. Therefore, when the electrical energy from the car battery is supplied to the motor, the coils create rotating magnetic fields that pull the conducting rods on the outside of the rotor along behind it. The spinning rotor is what creates the mechanical energy needed to turn the gears of the car, which, in turn, rotate the tires. Well, that's about the working part. Now about the motors. There are different types of electric motors used in the automobile industry. When it comes to electric vehicles, there are 7 types of motors, with each having its own strength and weaknesses. They are: brushed DC motor, brushless DC motor, permanent magnet synchronous motor, induction motors, switched reluctance motors, synchronous reluctance motor, and axial flux ironless permanent magnet motor. Now let's see how these motors are different from one another, starting with the brushed DC motor. Brushed DC motor is one of the simplest types of DC motor. It uses brushes to transmit current to the motor winding through mechanical commutation. The armature or rotor is an electromagnet, the field magnet is a permanent magnet. This motor does not require any controller to operate or vary the speed. The advantage of these motors can be the ability to provide maximum torque at low speeds. On the other hand, the disadvantages are its bulky structure, low efficiency, heat generated by the brush, and the associated drop in efficiency. The heat is also difficult to remove as it is generated in the center of the rotor. Because of these reasons, brushed DC motors are not used in EVs anymore. Cars like Fiat Panda Elettra used a series DC motor. It is a DC motor with permanent magnets. It is called brushless because it does not have a commutator and brush arrangement. The commutation is done electronically in this motor because these motors are maintenance-free. They have traction characteristics like high starting torque, high efficiency around 95 to 98%, and are suitable for the high power density design approach. Brushless motors are the most preferred motors for electric vehicle application due to their traction characteristics. These are useful for use in small cars requiring a maximum of 60 kilowatts of power. The disadvantages are a short constant power range, decreased torque with an increase in speed, high cost because of permanent magnet. Cars like Toyota Prius used a brushless DC motor. In this motor, there are permanent magnets on the rotor. Like brushless DC motors, these motors also have traction characteristics such as high power density and high efficiency. Permanent magnet synchronous motors are available for higher power ratings. It is also expensive as compared to other motors. The advantage of this motor is that it can operate in different speed ranges without using a gear system. It is efficient, compact, suitable for in-wheel applications. It also has high torque even at very low speeds. The disadvantage is that the huge iron will lose at high speeds during in-wheel operation. Most automotive manufacturers use these motors for their hybrid and electric vehicles. For example, Chevrolet Bolt EV, Ford Focus Electric, Nissan Leaf, and BMW i3 use permanent magnet synchronous motors for propulsion. The induction motors do not have a high starting torque like DC series motors under fixed voltage and fixed frequency operation. But this characteristic can be altered by using various control techniques like vector control or field-oriented control methods. By using these control methods, the maximum torque is made available at the starting of the motor, which is suitable for traction application. Squirrel cage induction motors have a long life due to less maintenance. These motors can be designed up to an efficiency of 92 to 95%. The drawback is that it requires a complex inverter circuit and control of the motor is difficult. Induction motors are the preferred choice for performance-oriented electric vehicles due to their cheap cost. Tesla Model S is the best example to prove the high-performance capability of induction motors. Toyota RAV4 and GM EV1 also used this motor. Switched reluctance motor is a category of variable reluctance motor with double saliency. Simple and strong in construction, the rotor of this motor is a single piece of laminated steel with no windings or permanent magnets on it. This reduces the inertia of the rotor, which helps in higher accelerations. The robust nature of this motor makes it suitable for high-speed applications. It also provides high power density, which are some essential features of electric vehicles. The biggest drawback of switched reluctance motor is complexity in control and increase in switching circuit. It also has some noise issues. Synchronous reluctance motor is a synchronous electric motor, the torque of which is due to the inequality of magnetic conductivities by quadrature and direct axis of the rotor, which has no field windings or permanent magnets. Currently, this type of motor is becoming very popular as an alternative to electric as well as hybrid vehicles, due to its easy and strong construction. The main advantage of this motor mainly depends on the non-existence of rotor cage losses, by allowing a higher permanent torque than the torque of an induction motor of the same size. This motor is the most advanced motor used in EVs. It has an external rotor with no slots. The use of iron is avoided here. The stator core is also absent to reduce the weight of the machine. The air gap here is radial field type, providing better power density. A notable advantage of this machine is that the rotors can be mounted on the lateral sides of the wheels, placing the stator winding on the axle. The slotless design improves efficiency by reducing copper losses, as more space is available. Renovo Coupe used this motor. According to the number of motors used in vehicle and their configuration, existing powertrain EVs can be classified into two types, including the centralized single-motor driven powertrain and the distributed multi-motor driven powertrain. The centralized single-motor one-speed driven powertrain is the most common structure in modern EV. Some EVs are focused on distributed multi-motor driven powertrain, and it is mainly classified into three categories: dual-motor powertrain, triple-motor powertrain, and four-motor powertrain. Let's start with single-motor configuration. It's relatively simple to understand the single-motor system. There is a single motor that drives the car. It is the motor that is charged and produces torque to the engine. In the single-motor configuration, the electric motor is mounted as front-wheel drive. There is also a differential as well that allows the wheels to rotate at different speeds. The motor converts the electrical energy received from the battery into mechanical energy, which enables the vehicle to move. It also acts as a generator during the regenerative process, which sends energy back to the energy source. Some Tesla EVs, and Polestar 2, comes with a single-motor front-wheel drive, and there is also a dual-motor all-wheel drive version. The electric range of this car is 425 kilometers, with a top speed of 160 kilometers per hour. Fewer components needed to create a single motor system, an adapted conventional transmission used, which makes it all in all cheaper to build. This makes it a less expensive option for consumers, which is always a good selling point for the eager buyer. It's also a better option for those who are new to the electric car, as it has a slightly different feel than a regular gas-powered car. It might not be as efficient as a dual motor system, simply because it lacks the second motor to create power. Braking won't feel as normal as a driver is used to, while the transmission is downshifting. To put it simply, the single motor system provides enough power to suit most individuals. When it comes to a dual motor system, you can expect to have a pair of motors that are placed in different spots of the vehicle. It's relatively clear that a car with two motors should be able to offer more horsepower behind the wheel. The combination of the torque from both motors ensures that there is a significant boost in acceleration for the driver. It is important to note that the same is also true for a single-motor electric car. However, a dual motor is going to outperform a single motor in terms of efficiency and speed at a higher altitude. With the AWD system and the dual motor, the car is able to distribute the horsepower and maximize the torque levels in immediate response to the road conditions. In this system, two motors are provided one on each axle and are coupled through planetary gear, and the torque is coupled through shaft fixed gear. Front and rear motor drives are supplied by one or sometimes two different battery packs. By using two-motor, two-axle configuration, it is possible to choose different power and torque sizing for the drives, and also to adopt different gear ratio for the gearboxes. You can check out this performance table for the two traction motors for front and rear gear ratios. The use of two traction drives improves the total tractive effort delivery in the whole speed range with respect to a single drive of the same total power rating. The main reasons for having more than one traction motor is that the additional degree of freedom in vehicle torque vectoring for enhancing traction and stability control, and the increased reliability of the overall traction system. Tesla Model 3 comes with the option of dual motor all-wheel drive system. It has two independent motors for improved redundancy, each with only one moving part for minimal maintenance and maximum durability. Unlike traditional all-wheel drive systems, they digitally control torque to the front and rear wheels for far better handling and traction control. The electric range of this car is 576 kilometers with the top speed of 260 kilometers per hour. The dual motor system allows for the car to speed up more quickly than ever before, while also having the ability to stop quickly. There are little to no gear shifting feels to the driver, leaving you with a smooth drive. One of the motors can be used to power up the car, while the other set of batteries can be recharging. This gives the user the ability to travel further without worrying about charging up. Dual motor systems are going to be more expensive due to the simple fact that they are more complicated to put together, and there is a lack of standard transmission. The overall control software is going to be slightly more complex than a single motor system. In this system, one motor is being placed on the front axle, while two motors fitted to the rear axle, thus making the car all-wheel drive. The two motors drive each wheel of the rear axle to improve efficiency and are solely responsible for powering the car in normal driving conditions. The third front-mounted motor comes to life when the driver needs more performance. Each of the electric motors mounted on the rear axle drive torques directly to the corresponding wheel through a single-speed transmission. That's what's called electric torque vectoring, and it eliminates the need for a mechanical differential. This exponentially enhances the all-wheel drive system, and the cars have improved handling, stability, and grip. They stay true to tradition, the driving feel of the cars being focused on the rear. This powertrain feels sportier than your everyday car and are very eager to drift. Audi revealed their latest version of the company's first mass-production EV, in the shape of the e-tron S, and its sportback twin. It is the first EV with a three-motor powertrain. Tesla Model S and Model X also used the three-motor powertrain. With a dedicated motor at each corner, the super-handling all-wheel drive system can precisely apply either positive or negative torque individually to each wheel. This opens the door to torque vectoring and full-time active yaw control, something that will make consumer EVs safer and more energy efficient. For motors means proper torque vectoring. Usually, as you turn a corner, the inside wheel and the outside wheel are rotating at the same rate. With torque vectoring, the outside wheel can get more power, pushing the car into a sharper, tighter turn. An EV with 4 electric motors can also be faster and more responsive, as it is adjusting torque electronically by how much power goes to each motor rather than mechanically. Things get even more flexible if you use 2 electric motors for each pair of wheels rather than one. That way, you can use two smaller motors rather than one big one, on an axle, and split them out to the sides of the vehicle. It'll arguably be even more efficient when in-wheel electric motors start to make it to production vehicles. Then the majority of the motor is actually contained within the wheel itself, further pushing the hardware out to the periphery of the car and freeing up even more space in the body for more practical uses. So what do you think about these powertrain systems, which are best for EVs to provide a better driving experience? What are your thoughts?